we can move to the next speaker, which is going to be Simona Paoli. And Simona from Leicester University, and she will talk us about weekly globular double categories and weak units. And Simona, whenever you feel like, you can share your screen.
Yes,
and take the stage.
Thank you very much. So give me just a second to bring out the slides. Okay. So I'm actually less used to Zoom than most people because we are not allowed to use Zoom in Leicester. So how do we do this? Okay, share screen. No, I don't know why. Something, okay. Okay, is it shared now?
I can see your screen.
Yeah, is that okay?
Yeah.
You can or you cannot?
I can.
You can, okay. Right, so, and I guess I should put this in full, maybe. It's like this, good?
It seems perfect to me.
Okay, right. So I can start, right? All right, so thank you. I can start, yes?
Yeah, okay. Whenever you want.
Thank you very much for the invitation. It's my first ItaCa meeting, and I'm very impressed by this new enterprise. Okay, so this talk is about two-dimensional higher categories. And as you know, the classical notion in dimension 2 is the one of bicategories due to Benabou. But higher category theory has seen the development of various other approaches to higher categories, which were prompted by questions in different areas of mathematics, such as homotopy theory, mathematical physics, logic, and computer science. And in particular, when n is equal to 2, this gives you various other notions of weak 2 categories. And some of these notions have been directly compared to bicategories. In some other cases, the comparison is more indirect, maybe via the homotopy hypothesis. But anyway, we know that there are many different approaches that you can take, particularly also in dimension 2. Now, a class of models that I've been studying in particular depth are the Segal-type models. And I have studied 3 of them, in fact, in all dimension, as you know, but in this talk, I will stick to dimension 2. Historically, the first one is the one of Tamsamani. So Tamsamani 2 categories denoted with TA2. Then later with Pronk, we introduced weakly globular double categories, which are in particular a full subcategory of double categories. And later I introduced the third model called weakly globular Tamsamani 2 categories that encodes these 2 special cases and which acts as a context in which to prove comparison theorems among the other 2. So there are functors connecting these 3 models, and these 3 models are suitably equivalent. Further, with Pronk, we also established a direct comparison between weakly globular double categories and bicategories. Now, another model of weak 2 categories is due to Joachim Koch, and it's called fair 2 categories. And it's based on the idea of encoding strictly associative compositions, but weak units laws. And so this model has attracted my interest for a very long time for a very specific reason, which is that there are 2 structures in fair 2 categories and in weakly globular double categories, which are very similar. Namely, the weak units in a fair 2 categories form an equivalence relation. And there is a structure in weakly globular double categories which forms an equivalence relation, which is the category of objects and vertical arrows. So it's very, you see the similarity and you want to ask, and this is really my motivating question, can we find a direct comparison between fair two categories and weakly globular double categories? Now, I have already mentioned that both of these models are suitably equivalent to bicategories. So you may think at first that such a question is somewhat trivial or not interesting. But what I really mean, and what I did in my work that I'm presenting today, is to find a direct comparison, which has nothing to do with the non-equivalences of fair two categories and weakly globular double categories with bicategories. Okay, so this is what I have done. And why is this interesting? First of all, because it highlights some new properties of weakly globular double categories, and in particular, it highlights how the weak globularity condition, precisely the structure of objects and vertical arrows being in equivalence relation, is about weak units. The second reason, which is even more important to me, is that I believe that this direct comparison is a good first step towards higher dimensional generalization. I'm not claiming that these higher dimensional generalizations are trivial, nor they are done yet, but I think this is a way towards it. Okay, so I hope this is explaining the motivation for what I'm going to talk about. All right, so I want to give some background about the Segal-type model. I was looking at the participant lists, and I'm just wondering if I'm just making people bored, because I know many of you have heard me talking already about the Segal-type model, but I see at least some new names. So for sake that I think maybe not everybody is familiar with the simplicial background, I'm going to go through quickly some of this background to explain at least the definition of weakly globular double categories. So a simplicial object in C comes equipped with certain maps called Segal maps, which are constructed from a commuting diagram like this, where these are the phase operators indicated. So there is a unique map from xk to the limit of the bottom part of this diagram, which is this iterated Pumbacks. These are called Segal maps, and they are very useful because in particular, they characterize the essential image of the nerve functor. The nerve functor goes from internal categories in C to simplicial object in C, and it has this shape. So you can see that a simplicial object in C is in the essential image of the nerve, if and only if all the Segal maps are isomorphism. This simple observation is really the starting point of the sort of simplicial approach to higher category theory. Now, so what are weakly globular double categories? We start from a simplicial object in cat, and first of all, we impose that all the Segal maps are isomorphism. And by what I have just said, it means that we have an internal category in cat, so a double category. Next, we imposed what I call the weak globularity condition. So we ask that X0, which in a double category we can think of as category of objects and vertical arrows, is an equivalence relation. So if you think homotopically, that's the same as a groupoid with no non-trivial loops. And in particular, this means that X0 comes equipped with a map from X0 to the discrete category on its set of connected components, and this map, which I denote gamma, is an equivalence of categories. Okay, so the way to think about this is that if you think about a strict two category, then this X0 would be discrete. Instead, in the weakly globular approach, we replace discrete, that is the globularity condition in a strict two category, we replace it with weak globularity, which means homotopically discrete. An equivalence relation is a category which is just equivalent to a discrete category. And the last condition is what I call the induced Segal map condition. So this map gamma induces a map from this iterated pullback to this one, and we require that this map is an equivalence of categories. So how to think about this structure? So the set underlying X0D plays the role of set of objects, okay? And the induced Segal map condition is what regulates the behavior of the compositions. In the bi-category corresponding to a weakly globular double categories, the set of objects is the set underlying X0D, and all the coherence data come out exactly of this induced Segal map condition. In particular, notice that in this induced Segal map is injective on objects, and it is always fully faithful, sorry. And so to require that this is an equivalence of categories is the same thing as to require that it is essentially surjective on objects. So given an object in here, and what is an object in here? It's a staircase of horizontal arrows where the source and target maps live in the same connected component. Then you can lift this. To an object of this one, which is a truly composable sequence of arrows. And these lifts have to be isomorphism. Okay, so these squares are vertically invertible. Okay, so I hope that this gives a good recap of this definition. I want to mention another couple of features of weakly globular double categories, which is the truncation functor and the home category. So the truncation functor is a functor from weakly globular double categories to cat, which is obtained by applying level-wise the isomorphous classes of objects functor from categories to sets, okay? And because of this induced Segal map condition, right, when you apply the isomorphous classes of objects functor, if you apply it to this type of iterated pullback over a discrete object, P preserves pullbacks over discrete objects. It's a fairly immediate thing to see. And therefore, when you apply this P level-wise, you find the nerve of a category. Here I'm abusing notation. I'm calling interchangeably categories and nerves of categories by the Segal condition. Okay, so we have this truncation functor, and this is what you would call, in terms of bicategories, you would call this the kind of fundamental category. And the other notion is the home category. So you look at this map from X1 to X0 cross X0. So these are the source and target, and then you apply gamma, and you take the fiber at AB of this map. Okay, this is a category, which is the home category corresponding to this A and B. So why do we care about these two notions? Because with these two notions, we can now give a definition of two equivalents in weakly globular double categories. So we say that a functor here is a two equivalence if for all A and B in X0D, this is an equivalence of categories. And if after we apply this truncation functor, we also find an equivalence of categories. So how do you want to think about this? This is a two-dimensional version of a functor which is fully faithful, so that would correspond to condition 1, and essentially subjective on objects, and that corresponds to condition 2. And just as a small technical remark, in case you are wondering, you can weaken this condition 2 a little bit. Okay, so we have defined weakly globular double categories and two equivalences. Okay, now I want to make a jump and come to the Koch model. We will come back to weakly globular double categories, but I'm just covering all the background before talking about the new results. So Joachim Koch started first considering the idea of colored category. So that's a category with a subcategory containing all objects, and the arrows of W are called colored arrows. The morphisms have to be color preserving functor. And you can apply the same ideas to free categories and to graphs. So a colored graph means that some of the arrows are colored. A free colored category on a colored graph, you take the free category, and then W is the free category on the colored part of the graph. Then the thing is that you apply this notion to ordinals. Ordinals are categories, so you have a corresponding notion of colored ordinal as the free colored category on a linearly ordered graph, colored graph. And we denote these finite non-empty colored ordinals with T And we can use this notation because you remember an ordinary ordinal, you can represent it as a series of dots where I less than j means that you have an arrow from I to j. So you do the same thing, but if an arrow is colored, you put a link. And the morphisms are the usual for the dots. And if you have a link, you say that the link can be set, but not be broken. You also have a functor from T to delta, which contracts all the link. And this is quite a useful thing to have around. So the other idea that Koch uses is the idea of semi-category, which I think was already in the literature before he introduced his model. So that's the same thing as a category, but without identities. And you can use something similar to the simplicial description for it if you restrict to delta mono. So delta mono is obtained by removing the degeneracies in delta. So if you have a functor from delta mono up to set, you can still have Segal maps. And if all these Segal maps are isomorphisms, that precisely gives you a semi-category. And a colored semi-category is, again, a semi-category with a sub-semi-category comprising all objects. Okay, so what Joachim did, he put all these three ideas together and gave the definition of what he calls the fat delta. So the fat delta is the category of all finite, not empty, colored semi-ordinals. And it can be naturally identified with T mono. Okay, so in Joachim's model, the fat delta plays a similar role that the delta plays in the Segal-type model. And you will see that there are really a lot of similarities in how the definition goes. So before I carry on, let me just mention that this pi functor from T to delta gives rise to a functor from T mono, which is the fat delta, to delta mono, which is included in delta. And this composite is the usual inclusion of delta mono into delta. Further, there are two other inclusions of delta mono in the fat delta, one interpreting a semi-ordinal as a colored semi-ordinal with nothing colored in this way, but you also have an inclusion somehow in the other direction, interpreting a semi-ordinal as a colored semi-ordinal with everything colored. Okay, so this fat delta is a very interesting category, and so in the work that I have done, I've also highlighted some other properties of the fat delta, which seems to be new. Okay, so the central definition for us is fair two categories. I mean, Joachim had this definition for any n, but in this talk we stick to n equals 2. So we start with categories where the colored arrows for us are the equivalents of categories. And we say that a fair to category is a color preserving functor from the fat delta up into cut, which preserves discrete objects and pullbacks over discrete objects. Okay, so Koch uses this suggestive notation. So the X corresponding to the dot is the object, the X corresponding to the two dots are the arrows, and the X corresponding to the links are the weak identity arrows, or weak units. And what is this condition of preserving pullbacks over discrete objects? Is basically the analog of the Segal condition. So for example, if you have a push out in delta up of this, then you want to have this pullback in cut. Okay, and what this particularly implies is that, remember, I talked about the two inclusions, horizontal and vertical, of delta mono up in delta up. This Segal condition implies that the arrows and the weak units are semi-categories. Okay, so they come equipped with a composition which is associative. So that's the first thing to bear in mind. The other thing that Koch proves is that the two maps from U to O coincide. Okay, so in fact, what it shows is that there is a sort of way to present, to give the data of a fair to categories, which is quite useful in practice and somewhat maybe more intuitive. It's enough to give a Fair2 category, it's enough to have the following data. Okay, so you want to have an object of arrows, an object of objects, an object of weak units, which are related to this diagram. Okay, and this diagram needs to commute. Then what you want to say is that you have a semi-category structure on U and A. So here I didn't have a lot of space, but what I mean here is that this U and A comes with compositions which are associative, and you have a semi-functor. Again, I didn't write the compositions, but it's kind of implicit. And the third condition, which is really the preservation of colors, is that these two maps, as well as these composition maps, are equivalencies of categories. Okay, so this is a more it's a less concise way of giving the data for a Fair2 categories, but it is something that is actually quite useful if you have a structure and you want to prove that that something is a Fair2 categories. So basically these conditions here, so A and B give you the Segal condition, and this condition C is the preservation of colors. Okay, so the preservation of colors is the one that somehow encodes the weakness in your structure. And this condition here, this data here, encodes the weak units. Now, notice in particular that saying that these two maps are equivalencies of categories, O is discrete, so it means that U is an equivalence relation. It's a category equivalent to a discrete one. Okay. All right, so is there a way to talk about two equivalences in Fair2 categories? Yes, indeed. I cannot remember if this definition was in the original Koch paper. I'm sure that Joachim knew about this. In any case, it's very easy. So you do the same thing that you do for the Segal-type models. You take the isomorphist classes of objects functor and you apply it level-wise for any objects of delta mono op. And similarly for the home category. Okay, you take the fiber at x0, at AB of this map. Now x0 for us here is discrete. And then you give the definition of two equivalents as being a map in Fair2, which is locally an equivalence. And after you apply the truncation functor, you have an equivalence of categories. Okay, so as you see, these two definitions of the Segal-type models and of Fair2 are really very, very similar. We have the structure of weak units, which is reminiscent of the x0 in the weakly globular double categories. So how now we are going to make these two structures talk to each other and be compared. So in order to do this, I have to tell you a little bit more about the Segal-type models, okay, because I need some technical tools. So I have told you so far about Cat2 weakly globular, and now I want to tell you about this model, which is bigger, and it's very simple idea. The definition is as for Cat2 weakly globular, but you take away the Segal map condition. So you don't ask all the Segal maps to be isomorphous. So we are left just with the weak globularity condition and the induced Segal map condition. Now, if x0 was discrete, okay, then this would give you TA2, right? So you see that this model is really a generalization of these two. So why do I want to speak about this? Because this TA2 weakly globular has been a very useful context for comparison. And you can build a functor from TA2 weakly globular into a class of pseudo functors from delta op into cat, which is very important in the Segal-type models. And I call this class of Segalic pseudo functor. Now, just a small piece of background about pseudo functor from delta op to cat. If you take any old pseudo functor from delta op to cat, you cannot, in general, talk about Segal maps because a diagram like this would only pseudo commute. But if you ask that H0 is discrete, then it makes sense to ask, then this diagram commutes, so it makes sense to talk about Segal maps, okay? So a Segalic pseudo functor is a pseudo functor from delta op to cat such that, first of all, this X0 is discrete. So that means that we can talk about Segal maps, and then you require the Segal maps to be isomorphous. So why is this category interesting? Because if you start from your weakly globular time spanning two categories, there is a sort of fairly straightforward way of building a pseudo-functor from delta up into cat. The pseudo-functors at the level of objects is defined by X0D, X1, and then this pullback. And then you have to define all the structure maps, okay? So if you start doing this by hand and you don't think about other tools to use, it becomes very messy. But fortunately, there is a smart way to do this, which is to use the notion of transport structure along an adjunction. And then you can prove conceptually that this gives you a pseudo-functor. And because of this definition, you see that by construction, this pseudo-functor is Segalic, okay? So this transport structure gives you a functor from tattoo weakly globular to Segalic pseudo-functor. So the name TR is because it's transport, is built by transport structure, and 2 because I also had this functor for n bigger than 2. Now, the main point here is that you know that there is a classical strictification functor from pseudo-functors into strict functor, which has been studied by a lot of people in various different ways. And what you can show is that if you apply this strictification to a Segalic pseudo-functor, you find weakly globular double categories. This is a very important fact. The form of the strictification that I have used for this proof is the one of that was initially studied by John Power and also refined later by Steve Luck. That is a very explicit form that allows us to identify the characteristics of this strictified thing as a weakly globular double categories. All right, so how are we doing with time? How much time do I have still? 15 minutes?
I would say something like 15 minutes.
All right, I have to speed up because I have just finished the background. Oh dear. So the fundamental observation that is the starting point of this work is what happens if you restrict this transport structure functor to Cat2 weakly globular. So I remind you that Cat2 weakly globular sits inside here. So if you have a functor defined in here, you also have a functor defined on Cat2 weakly globular. And something very interesting happens. What happens is that when you restrict so let me pull out the proposition. When you restrict the transport structure functor to Cat2 weakly globular, you find a Segalic pseudo-functor which has some additional characteristics, and I call it strong. What these characteristics are is that when you restrict to delta mono op, you find an actual functor. Okay, so the restriction from strong Segalic pseudo-functor to delta mono op gives you an actual functor from delta mono op into cat. And how do you prove this? Well, it's a matter of showing that this object is a functor from delta mono op into cat, which is the same thing as a semi-simplicial object. So all you need to show is that these maps satisfy the semi-simplicial identities. Do we know what these maps are? Yes, indeed, because by transport of structure, these maps are explicitly built by, so I don't manage to use the pointer. So for example, delta I prime is given by these three composites. My pointer doesn't work very well. These three composites, which are built from the induced Segal maps and their pseudo inverses. Okay, so this is just explicit the form of the of these maps by the transport structure. Now, the observation is that because these induced Segal maps are injective on objects, mu k hat is equal to the identity. So there is a cancellation here, and then this is what makes the semi-simplicial identities to hold. Okay, so it's really the form of these induced Segal maps. And notice that if you were in tattoo weakly globular, then this xk would not be equal to this. So there is no way that this injectivity on object would hold. But if we are in a weakly globular double categories, that's the case. All right, so now we have basically all we need to build our functor from cat2 weakly globular to fair2. And we build this functor, we show that it preserves two equivalences. So remember earlier we said Koch gives a useful criteria to just build a fair two categories. So we have a set of objects, which will be our discretization. The arrows will be x1. The identity arrows are x0. The identity arrows are the category of objects and vertical arrows. You have this commuting diagram because sigma 0 delta 1 is the identity. So that holds. What do we need next? We need a semi-category structure on x1 and on x0. Do we have it? Yes. Precisely by this proposition that says that this is an actual functor from delta mono op into cat. Okay, so that's where you get this associative composition. What is left? We need the two map from x0 to x0d to be equivalences of categories. They are because of the weak globularity condition. And finally, we need these maps, these composition maps, to be equivalences of categories. And that's something that you easily prove, okay, from the properties of weakly globular double categories. So that's it. We have built a fair two category from a weakly globular double category. And in these fair two categories, the objects of objects is the discretization. The arrows are the arrows. And x0 plays the role of weak units. So this is one part, but now we have to go the other way around, okay? We have to build now a functor from fair two categories to weakly globular double categories. And this is more involved technically. So what we do first, we build a functor from fair two categories to these Segalic pseudo-functors. And the form of these objects is what you would expect. The proof that this is a pseudo-functor is quite involved. And it relies on certain pretty technical properties about both the fat delta and fair two categories, which as far as I can see, were not in the literature. So I had to work pretty hard, but this is something that you can show. Then once you are here, the obvious thing to do is to apply the strictification, right? Because this is in particular a Segalic pseudo-functor. So when you strictify, you get into weakly globular double categories. So we have these two functors. Now the question is this what gives us a suitable equivalence, at least up to homotopy? And that's what the theorem says. So if you localize this with respect to the two equivalences, you do find an equivalence of categories. So what is involved in the proof of this result? We have the definition of the functors, but we need to now make sure that if we start from X, there is a zigzag. In fact, we produce an actual map between X and R2, F2X. And if we start from Y, you produce a zigzag of two equivalences between Y and F2, R2Y. Now, this proof is not trivial because somehow to do the second part, I had to go outside of the category fair two. Let me first go through the first part. I'm not going to give full details, of course, but just at least some of the ideas. So given a weakly globular double categories, I built a pseudo-natural transformation from T2 F2X to X. Again, it's something quite technical. I don't think I would have the time to illustrate the details. But I want to stress that once you have this, the rest follows formally, because by adjunction, then you have a map from the strictification of this into X, but the strictification of this is by definition R2, F2X. And this map is a level-wise equivalence of categories. Now, a level-wise equivalence is in particular a two equivalence. So we are done, okay? Because that means that when you localize, this is isomorphic to this. So the technical bits is this part, and the rest follows formally. The other way around is more tricky because what I showed is that first you have a pseudo-natural transformation like this, and the level of technicality is more or less like the previous part, although in a slightly different context because you have pseudo-functors from the fat delta rather than the delta. But then basically, so what you want to do, you want to apply stratification again because you want to use your adjunction. But when you do this and you apply stratification to this thing, you end up outside of the category FAIR2. And where you end up is in a category which I call FAIR2 weakly globular. So at first I was a bit annoyed by this, but then somehow I think this is not so surprising. You know, if we go back to the Segal-type models, when we started looking at the comparison between this model and this model, to actually do the proofs, it really is helpful to go into a bigger world where you have a weakly globular version for both of them, which generalizes both of them. And somehow something very similar is happening here. So if you want to do the proofs, you have to move into a bigger context. And in this bigger context, which I call FAIR2 weakly globular, you establish a zigzag like this. Okay, so I don't have time to tell you what is FAIR2 weakly globular, but the idea is that it's like FAIR2, but instead of having a discrete set of objects, you have homotopical discreteness, and then you have the other conditions which are similar to a FAIR2 categories. It's a weakly globular version of FAIR2 categories. Okay, but then what do we do with the zigzag? Remember that in the end, we want a zigzag in FAIR2. We need a zigzag in FAIR2. Well, fortunately, there is a functor from FAIR2 weakly globular to FAIR2, which preserves two equivalences, and it is identity on FAIR2. So once you have this zigzag, you apply this functor, and you are done. Okay. I'm not claiming that there is no way to do this without this FAIR2 weakly globular, but this is the only way I found. And in my view, it's not so surprising. I mean, sometimes you enlarge this context. I think the notion of weak globularity is really a useful tool in, in higher category theory to have more freedom in the way you handle these objects. Okay, so this is pretty much the end. So just a quick summary. We have in the literature several models of weak to categories in addition to the classical bicategories of Benabou. And I've been concentrating here on two different classes of models, the Segal-type models, which include Tamsamani model, weakly globular double category, as well as this model that puts them together. And then Joachim-Koch model of FAIR2 categories, which models weak to category with strictly associative composition, but weak units law. So the topic, the main result, is a direct comparison between weakly globular double categories and FAIR2 categories, made of two functors between them, which induce an equivalence of categories after localization with respect to the two equivalences. This comparison does not use in any way the equivalence of these two models with bicategories. So it's something which is built completely directly, which brings out a lot of new ideas and new technique. And in particular, it brings new light on weakly globular double categories as encoded in the weak units. This equivalence relation of weak units, which was highlighted in the Koch model, is precisely what the weak globularity condition is encoding. And I hope that this will be a good starting point for high-dimensional generalizations. It's not straightforward, it's not trivial, but I think there is potential there for further development. I think that's all. There is a preprint, which I've put on archive. There are, I think, a few typos. I don't know when I will have the time to post a correction, but all the ideas and also all the references to the literature are there. I think that's all. Thanks for your attention.
Thank you, Simona. Thank you very much for your talk. We have our usual round of silent applause, and at the end of it, which means now, if people have, they can ask questions to Simona, and You can just unmute your mic.
I have a question, if I may.
Of course.
So first of all, thanks, Simona, for the nice talk. And so my question is sort of more related to your work overall as a whole, and it's the following. In a paper with Alexander Campbell, we show that the infinity category of ordinary one categories is reflective inside the infinity category of infinity categories. So to put it in more layman terms, the Folk model structure on ordinary categories is a Busby localization, can be expressed as a Busby localization of the Royal model structure for infinity one categories. And for infinity n categories, this can be iterated. So there's a way of discretifying or making discrete an infinity n category, thus obtaining something that resembles a weak n category. Have you ever thought or worked on comparisons between localization of infinity n categories and the models you developed for weak n categories?
No, I have not, but I would be very interested. So maybe I will contact you later with some, if you can give me some more precise references, because it looks like a really interesting possibility. Yeah, so let's, yeah, I'll send you an email. I would like to know more about the papers you're referring to. Yes, I mean, I really do believe there's a lot to do still about this relation between the kind of truncated models like the Segal-type models and the infinity ones. And I also think that this would be particularly interesting in the context of these Segal-type models. Especially now that there are also these new developments. Yeah, so I've not done it yet, but I would like to know more about precisely which papers you're referring to. So thanks.
Okay, thank you.
Well, thank you, Eduardo. Is there any other question? Okay, so if not, we thank again Simona. So thank you, Simona, for coming today and joining us. And let me thank again our first speaker of the day, which was Giacomo Tendas. And the morning session is over now, and we meet again later in the afternoon. This is going to be at 2 o'clock, and we will have